Hey, what's up? My name is Pavi, and if you've been following me for a little bit, you know that I've been pretty obsessed with creating a project all around voice-based biomarkers, essentially analyzing vocal fluctuations in your vocal cords to then diagnose a disease through simply recording a sound of your voice. So it sounds pretty crazy and pretty abstract, but I've actually built two systems regarding how you can analyze Parkinson's disease and Huntington's disease through analyzing voice fluctuations. So I want to go through how I built those projects and also why I built them. So this video is going to highlight a bit more about why, so really the problem of healthcare accessibility and how this project or these types of systems are actually going to tackle that, and also the code for how I built out my Parkinson's project. And then my second video, which might be a bit shorter, is really going to highlight how I went through the Huntington's project and really talk about feature extraction. So it is kind of a two-part series, if you will say, and if you're interested in it, I will link the other video down below. And I've also written a super in-depth article regarding my code and both of the projects, so you can check them out below. But let's kind of get into why healthcare accessibility is a huge problem and how voice systems can actually help tackle that. I actually want to start with talking about the problem of healthcare accessibility and kind of how it varies from country to country, because we typically think that healthcare accessibility is a problem that really does occur in developing countries, which is true, but it doesn't just happen in developing countries, it happens around the world. And every country almost has its own broken healthcare system, which is really just sucks. But there's so many different problems because it's such a multifaceted problem. So if we look at healthcare, when you think about healthcare, there's a lot of different portions to it. Think about medicine, prescriptions, drugs, diagnosing, supplies, right? If you think about those three main factors to it, and if you check out an article, which is the Hey Alexa, What's My Diagnosis article I wrote earlier, you'll actually see that breakdown that I talked about. So a lot of these problems happen. Certain countries have problems in all of these buckets, whereas other countries might only have it in one or two. Now, I want to give an example of the United States and Malawi, which are two prime examples of how healthcare accessibility varies based on country to country. So if you look at the United States, 16% of people in the US, almost 50 million people, live with no healthcare coverage or no insurance at all. And I guarantee there's a lot more than that, but that is just a number that is documented. So what that means is these people have to pay for every doctor visit they have, or every surgery, or anything related to their health, and those bills are really expensive. So either they have to pay for that if it's super serious, or a lot of them don't even end up going to the doctor. So we have yearly physicals we have to do, which are a great way to actually know if there are issues going on in your body, but they have to pay for them. So if they don't want to pay for it because it's super expensive, they won't go to the doctor. And so very simple health issues that might be baseline and to be treated within a week or two might actually end up being detrimental to their health and can cause, just compounding health effects. Now, obviously the price is a huge part of the United States issue and their broken healthcare system. But if you look at something like chronic illnesses, which is one of the highest, the US has one of the highest rates of chronic illnesses, they contribute to a majority of the healthcare costs in that country. For example, I think patients with chronic illnesses spend around 32% of their Medicare spendings all towards hospital fees and repeat visits, simply because they have this chronic illness and they have to go to the doctor constantly. But let's say that we brought in telemedicine into this. Now they don't have to go to the doctor very often. You don't have to pay for those hospital fees because you're doing everything online. But telemedicine and remote monitoring is a great solution for certain problems, but it does not target everything in healthcare accessibility. For example, now we're looking at another country. Let's look at Malawi, which is located in Africa. And Malawi actually over the past 2 years has had a super bad healthcare track. So what actually happened there is they have been running out of supplies. Very basic medical supplies like syringes, ventilators, gauze, cotton swabs, everything you can think of, they're essentially running out of it. And the reason behind this is a forex issue, which is currency exchange rate. And what's happening there is that that's one of the highest liquid asset markets, but Malawi is their currency is decreasing. So inflation is increasing. Therefore, the supplies of those medical supplies are increasing. So people are being told to bring their own syringes to be, given medicine at these healthcare centers. And all the healthcare centers are running out of supplies. So everyone has to travel hundreds of miles to these hospitals, this one central hospital that is now having overcrowding. So you can see that, the problem of cost in the US might be a problem in Malawi, but it's currently not the main problem. So healthcare accessibility is a very complicated bucket of problems. And it's difficult to find a solution that can be universal for all, because a diagnosing issue or diagnosing solution is not going to solve a supply issue. But there is an approach we can take to this, which is all about using AI to actually help with different parts of this problem. And I really focus on how we can use AI to help with the diagnosing problem and help specifically with the cost problem happening in the US. So I'll dive a bit deeper into that and why an AI solution actually makes sense for this. Now, Vinod Khosla actually talks about this a lot, and I'm a very avid believer of this as well. And it is that digital systems will probably override doctors in the next 2 or 3 decades. So think of it like this. Someday you might be in a village in India, and their doctor or their entire healthcare system relies on an AI system. Whereas at Stanford, they rely on cardiologists who, are Stanford cardiologists. They've been studying for 8 or 10 years. Now, the cardiologist is obviously an expert in that one field, but the AI might have 25 years of learning and experience of different healthcare issues and can then diagnose more accurately. So in the end, do you think that the AI system will diagnose more accurately or the cardiologist? Because I personally think the AI system will do it. Now, obviously, there's a lot more to that and a lot more layers to that. But on the surface, it makes sense, right? Because an AI system is going to have 25 years every single day of diagnosing and training. But it requires a lot of different data and a lot of different feature extractions that you have to do, which I'll talk about more in the next part of this video. But if you kind of compare how this would look in a status quo world, right? In a status quo world, you go to the doctor, and this is in a healthy area. You go to the doctor and you tell them what's going on. They monitor you. They do a lot of these visual tests, whether it be looking at your throat, your ears, your heartbeat, your breath, everything like that. They assess the situation. They provide a diagnosis. You go to the pharmacy, pick up your prescription, and then you get sent off, and then you do a little bit of follow-ups. Now, this actually doesn't happen in a lot of parts of the world because a lot of the parts of the world aren't as developed or don't have all these resources, like I mentioned. But this is what happens in a very clean doctor's environment. But instead of, sometimes these situations are a lot more complicated than we think, because you might actually need to go to the hospital after this and go get a super expensive test or an MRI scan. But a lot of areas in the world don't have this high-tech medical infrastructure and medical equipment, and instead they need a way that you can diagnose and you can evaluate how your health is currently doing non-invasively and remotely and accessibly. Hence why I've been looking at voice-based biomarkers and voice systems to analyze everything happening in your body through voice. Alright, so now I'm going to actually talk about Parkinson's and the project that I built. So I'm going to give a little bit of an intro and the features that I'll be analyzing, and then I will go through the code of how it all works. So with this particular project, the features are already extracted and the values are already given, and now we're trying to actually analyze what those values actually mean. Whereas with the second part, with Huntington's, the other project that I made, that project really focuses on actually extracting the features and then analyzing it. So for those of you who don't know, really quickly, Parkinson's disease, or PD is what I'm going to call it. PD is a neurological disorder which essentially causes a decrease in dopamine levels in your brain. Now this causes a lot of different issues within your body, whether it be tremors, stiffness, changes in your mood very quickly, because obviously you're decreasing dopamine levels, but also in your throat and how you talk. So you're going to have lower volume, you're going to have difficulty speaking or difficulty moving some of your muscles, and it might be a little bit more monotoned, again, leading back to the dopamine levels. So there's a lot of different features that we can extract through this, and a little rundown of some of the features that I'm going to be extracting or going to be talking about is essentially when you have average vocal fundamental frequency. So this is essentially all of the vibratory rates in your voice, like your signals. So when you're talking, all of the vibrations happening, and that is something that is analyzed through just how the vocal folds and vocal cords move, which are typically like that. That would be the vibrations. And there's a certain average that you have to meet. So for males, it's going to be around 100 to 150 hertz, whereas for females, it's around 180 to 250 hertz, which is like the normal average. We also have maximum vocal fundamental frequency, so that's the highest of those vibratory rates. And then you have the minimum of that, again, those are 3 different features that we're extracting. And then we also have jitter, which is essentially the percentage of time during the entire audio sample where the patient's frequency is varying per cycle. So when you think about waves. So your frequencies and your signals that you're extracting are going to look like waves. So you take one cycle, which is one wave, and the way that the frequency is going to vary based on each of those cycles is what the jitter actually is. And then we have multiple different variations of that jitter, which are just differences in those fundamental frequencies. And then we have variances in the shimmers, and also HNR, which is harmonic to noise reduction ratio, which is basically the ratio of noise to the tonal components in your signal. And then finally, a really important thing to note is the status. So the status is basically giving a number to the patients. So if you're given a number 1, that means you have Parkinson's. And if you're given a number 0, that means you're a healthy patient, because there's both of them. So now, let's finally get on to actually talking a little bit more about the code and how it all works. Now, I talked about this a lot more in an article I wrote, which I will write and add in the description. It was one of the first articles I wrote about the topic, and it explains how to understand the voice and why this is a good biomarker. But really quickly, a little rundown about why this is a good idea is essentially your speech carries a lot of information. And it tells you a lot of information about the speaker in so many different ways, right? Obviously, you get the linguistic content about what the person's saying. So you've been watching this video for probably over 7 or 8 minutes now, and you can kind of understand what I'm saying and what I'm trying to tell you. But also, you can understand their traits and their paralinguistic states, which is essentially their emotional stages, their age, and their gender. So for me, you can probably tell that I'm around a teenager because of the pitch of my voice. You can tell maybe I'm around a teenager age, and my gender is a female. And you can probably also tell my emotional state is very informative right now, but also kind of energetic, I hope. But in that sense, you can tell a lot by just what a speaker is saying. And all of these, if we're able to actually recognize them, break them down a little bit further, recognize them, and then analyze them, we can actually understand what is happening. Because a lot of your systems, specifically your respiratory system and your brain, so your nervous system, they connect to your throat and your voice box, known as your larynx. So we can actually analyze all these features and put them into a spectrogram, which is essentially a graph of the frequencies of a certain signal. And then if we can analyze that through CNN or through other systems, you're able to then identify what is happening in the person's voice and how can you relate that back to another system. Again, this is a very simplified version, but if you want to hear more, you can obviously read the article below. Okay, so now I want to go through the GitHub and also really quickly talk about the data set. So this is the data set in a CSV file. So this is what I mean when the features are already extracted. So here, for example, you can see the fundamental frequencies, the jitter, and then these are all the extra jitter components I was talking about. You have all the shimmer components, and then you can see the H&R, so the ratio, and then here's the status. So all the ones represent Parkinson patients, and all the zeros represent healthy patients. And then you can continue to see a little bit more about all the data. So after we kind of analyzed that, now it's time to talk about the code part of it. So you start off in the code where we're just kind of importing the libraries, obviously. And the second part is actually loading up the data set. So here, again, Parkinson's CSV. And here's where you can see the top 5 rows of the data set. So again, you have your name. So this name represents the number of the recording of that patient. And then obviously we have the fundamental frequencies, and then you can keep going. It's the same thing as the data. We're just checking if it was there correctly. And you can see that the top 5 people were all Parkinson's patients. So this next part is actually finding patterns and insights in the data by using the describe method. And here we can see, the count, the average, minimum, and then you can see standard deviations and the maximum. So with this, we can actually extract a few insights. And one of the main insights that I actually got from this is that we can see a normal distribution of the data set because the mean and the median are very similar. However, the mean actually is greater than the median, which means that there's going to be a few other outliers, but that is kind of just throughout the entire thing. Now, next, we're talking about and looking at a class imbalance. So this is us trying to see if there is a greater representation of people with Parkinson's compared to the healthy amount of patients. So is the data almost skewed in a way? So in this case, it is skewed. And the reason is because you see one is people with Parkinson's. About 75% of the entire data set is people with Parkinson's, whereas only 25% is people without Parkinson's. So it is skewed in that way. But that's just kind of how the data is. And then the next part of this, and again, this being a field where data is very limited, that is the best possible thing that we could have gotten. And next, here we're just checking for any missing values, and here we're all good. This is just a precautionary part of the project. And then this next part is actually looking at plot distributions of all of the features in the data set and in the code. So there's a lot of features. As you can see, if we scroll all the way up, there's a lot going on in here. But looking here, if we zoom in a bit, you can see that we have all of the features on both the X and Y. That's why there's so many plots here, because you're comparing every feature with every feature. So we can get quite a bit from here, even though it's very difficult to analyze. One of the main things is that the H&R, which is the harmonic to noise ratio, actually has higher numbers for healthy patients than it does for unhealthy patients, so for Parkinson's patients. And they can also see higher values in the vocal fundamental frequency in Parkinson's patient and not in the healthy patients. So when you actually extract all of these and look at all these insights, you can then figure out the major correlation between voice and between Parkinson's and healthy patients. And that's how you can then make further advancements in the field. So next here, we're just checking for any outliers for every single feature. So in this case, we have quite a bit of outliers, but considering that the total amount of outliers we have are 195, the total amount of observations we have are 195. Some of these numbers of outliers are greater than others. So in this case, 6 outliers for the shimmer isn't huge, whereas 19 outliers in the NHR are huge. And we don't know if those outliers are occurring for those healthy patients or the Parkinson's patients, but regardless, they are outliers. And that tells us also that, the data isn't exactly perfect and we need a larger data set and more trials to actually make this more concrete. Now, this next part of it is actually us making a heat map, and it's going to tell us more of the correlations between all of those independent features. So again, because there's so many features and you're comparing each with each, it's difficult to analyze everything. But how you'd kind of go about analyzing this is you'd be checking the colors because those represent the same amount of numbers. And if we're looking in this general area over here, you can see that we're looking at all of the jitter sections. So let's take a look at this dark orange section, all of the jitters and the component features to it. And then if you scroll down, they're correlated to these shimmer features. So then again, it helps us make correlations between all these independent factors and how they then relate to Parkinson's in healthy patients. And then this next part is really just training the model. So now that we've analyzed more about the features, it's about the model. So we're just splitting the data set into the training and the testing model. And then over here, we're essentially creating a random forest model, which how it basically works is you create these decision trees, a ton of them based on all the features, and then you're going to try to find the best and accurate method from all those decision trees. But to first do that, we have to figure out how many are the optimal number of decision trees to have. So in this case, we got 50, but we realized that 50 was the lowest number that we actually put into the data, or we put into the system. So just to double check that it's not the lowest number, we're going to change the parameters. Instead of 50 to 200, we're going to change it to 25 to 75. And we get that the optimal number is 51, which isn't too far off of 50, it's just one up. But it shows us that the optimal number of trees is going to be 51 trees. So after that, now that we know that it's 51, we're going to fit the model onto that optimal number of trees and try to get the accuracy. And then we create our little ROC curve. And from that, we can tell that the accuracy is around 94%. And we can really see that correlation. So now that we know that this is a correlation, it's really more about analyzing the features, which is why I spent a lot more time on the features than I did about actually testing out the model, because the features are going to actually help create more of those correlations and see what is causation, what is correlation, and how can we further advance that in using Parkinson's and voice analysis. All right, and all of that being said, that is how I created that Parkinson's project. A lot about features there, not really about feature extraction, but feature analyzing, and a lot about healthcare accessibility and why this is a valid solution for that problem, or at least a section of that problem. So I hope you enjoyed, and if you want to see how I created the Huntington's code, that's going to be a lot more focused on the feature extraction and then showing the code as well. And it'll be a lot less focused on the healthcare accessibility portion. It's going to be a shorter video, so if you want to check it out, that is the second part of this massive project that I've created. And that's about it. I'll link them all in the description box below. Thank you so much for watching. And if you have any questions, feel free to reach out because I would love to further continue this project. And a lot more is to come in the future with voice-based biomarkers for me.